Hi everyone, in this video we are going to review the combustion module. And so the way I do my reviews is I split them into two different sections. I have a context section, so that's mostly the memorization, so you need to know about air pollutants, you need to know about combustion, just whatever it is that I think you need to memorize and just have in your brain. The second section is the chemistry section, so that's more of the application side. And so this is usually the section that students find the most challenging. And so to kind of remedy that a little bit, at the end of the review we're going to do three of what I consider the most challenging problems on this unit or this module, however you want to call it, and then we'll just have basically three more examples for you to practice at home so that hopefully you can get an A on the exam, because that's the goal, right? All right, so the first thing we're going to do is just start off by reviewing that context section. So number one, context. So this is the memorization. This is what you just have to get down. There's no other way around it. The first thing we did is we talked about a combustion reaction. So now we've been reviewing this all semester, but at this point, we really need to have it down. And so essentially what we are very comfortable with is that we know we have a source of fuel, and we treat it with oxygen, and we create carbon dioxide and water. Now, this is considered a complete combustion reaction. If we said an incomplete combustion reaction, instead of CO2, we would just write CO. So it would be carbon monoxide instead of carbon dioxide. All right, so now what we've added in this specific module, or combustion module, is that we now know that this is an exothermic reaction. So when we write out our combustion reaction, we usually write the word energy right here at the end because it releases energy. If it didn't release energy, we wouldn't be studying it. All right, so that's the first thing. The second thing we looked at was just very simply or very globally I could refer to as energy transfer. So we talked about the first law of thermodynamics, how we can take one source of energy and transfer it to another source of energy. And we primarily did this in the context of power plants. So we talked about three different types of power plants primarily, which was our coal, we had our petroleum, and even our natural gas. But for the most part, they all followed a very similar schematic in which they took potential energy and they converted it to kinetic energy, and then they converted it to mechanical energy, and then electrical energy. So we know that the potential energy is what's stored in the fuel source, so stored in the bonds of the coal or in the bonds of petroleum. We know that they set it on fire, and then the energy released that was in those bonds is then released, and that goes into the boiler. And then the boiler tries to get as hot as possible, and so we turn our liquid water into gaseous water, and so we convert our potential energy into kinetic energy. From there, the steam flies through up to that turbine, makes the turbine spin, in which we convert our kinetic energy to mechanical energy. And at the very, very end, that mechanical energy just continues on through the generator, and the generator is able to create it, or I shouldn't say create, but transfer that energy from mechanical to electrical energy. And so that's essentially how that schematic works for the power plant. You should be able to draw it, you should be able to write it out, and you should be able to know absolutely every single station at which we're converting or transferring this energy. All right, now we talked about power plants a lot, okay, a lot. So the first thing was the schematic of how we did that, but the second thing is we talked about efficiency. And so we gave primarily two different methods of how to calculate something or how to figure out if a plant is efficient. And so you can multiply all the efficiencies together, or you can take your electrical energy produced and divide it by the amount of heat that was originally released from your potential energy. So there's two different ways. I would be familiar with both of them. Then we jumped into a huge section, which I'm just going to call fossil fuels. Now, we learned a lot about fossil fuels, so we need to be super careful with this and make sure we can divide it all out. So let's just break it down one by one. The first one is our coal. Now, what we know about coal is that this is our fossil fuel that's in the solid state, and we know that it releases about 30 kilojoules of energy per gram that is burned. Okay, the primary thing that we talked about with coal was mining and the different types of mining disasters, because that's the biggest harm for coal. All right, number two. The second thing we talked about was petroleum. So now petroleum was our second fossil fuel. We said it's the liquid state, and we know that it releases about 48 kilojoules of energy per gram burned. Now, when we talked about petroleum, we primarily focused on what is called the distillation tower. Okay, so that was the purification process where we take crude oil and we basically pump it into a section and separate it by boiling point, or separate it by size of the different hydrocarbons that are in that mixture of petroleum, or in that crude oil solution, we should say. All right, number three, the third fossil fuel we talked about was our natural gas. This one's pretty simple. We definitely know that it's in the gaseous state, right? Natural gas, it says it right there. But for the energy, we say that it actually releases around 50 kilojoules per gram burned. So it's our best source of energy when talking about our three primary fossil fuels. Now, the main thing we talked about for natural gas was actually fracking. And so we saw a lot of the advantages, but also a lot of the disadvantages. And for the people at home, if you've not seen the movie Gasland, I would highly recommend it. I think it is a very, very good source to see a lot more about fracking and actually visually see these examples. All right, the last thing we talked about for fossil fuels were the negative aspects, or the drawbacks, or the things that were not good when we use these fossil fuels. And we can break them down into three main categories. The first one is human health. I always want to know for each one of these, are there any way or any reason why we're going to have some adverse human health effects? That's super, super important. So if there are, you should know them. The second one is environmental harm. So we have environmental harm. Usually with environmental harm, we're just talking about groundwater contamination, but that happens for all three of them, and it's one of the worst things about all fossil fuels or using fossil fuels as a source of energy. And the last one we always talk about are greenhouse gases. And so for the first two, for coal and petroleum, primarily we're only referencing carbon dioxide when I say greenhouse gases, but for natural gas, which is essentially methane, we also have methane, which has that global warming potential of 21. We can't forget that. We still have to keep that in our brain, so that's definitely an issue. All right, so moving away from fossil fuels. After we talked about fossil fuels, we've talked about different sources of energy, or specifically oxygenated fuels. So oxygenated fuels, well, there were two main ones that we focused on, and it primarily depends on what type of engine you have. So for me, I drive a Camry, and so in my car, the only type of alternative energy source or fuel source I would be using would be ethanol. So the first one we talked about was ethanol. Okay, ethanol, I would expect you to know the formula is C2H5OH. Okay. The first thing we talked about with ethanol, or the primary thing we talked about with ethanol, is that it releases about 26.8 kilojoules of energy per gram. Now, ethanol is a great substitute for octane or your gasoline, but only for internal combustion engines. Now, alternatively, let's say you drive an awesome truck, so some huge beast truck, right? Something fun, and you use a diesel engine. So instead of ethanol, because you can't use ethanol in a diesel engine, you would use biodiesel. So we talked about biodiesel a little bit in this class. I do not expect at all for you to know the formula. That is way, way, way too complicated. So for me, biodiesel is just beautiful. That's all I need to know. All right, so now your energy source of biodiesel, it's about 37.8 kilojoules of energy released per gram burned. So the two things that are super, super important about this is that these oxygenated fuels burn cleaner, but they release less energy. Now remember, we're comparing everything, so I'm just going to write relative to gasoline, and gasoline is primarily octane, so a lot of times when we reference this, we just say octane. And just to give you a point of reference, octane has an energy source of about 42 kilojoules of energy released per gram burned. And so for all of these sources, the oxygenated fuels are definitely giving us or providing us less energy per gram per gram burned, but it's definitely burning cleaner. And when I say burn cleaner, that means that we're releasing less carbon monoxide and less carbon dioxide into the atmosphere. So it's much, much better for our environment. But if you want to drive a big beast truck or maybe a Corvette or something like that that's really, really fast, these alternative fuels are not really the best. Okay, so now after that, we started talking about gasoline specifically. So instead of our oxygenated fuels, we just focused on gasoline. Now we know that gasoline usually has anywhere between 5 and 12 carbons in the source. We focused with gasoline, we talked about those octane ratings, so make sure you're very comfortable with the octane ratings and make sure that you could describe what the actual octane is, or the gasoline is. So for example, if you have something with ethanol and it's 15% ethanol, you would know it's E15. If you know something is 20% biodiesel, you would call it B20. But those ratings and those words, you need to know those abbreviations. All right, we also talked about knocking. So knocking was that really fast spark or an unexpected spark that blows up your internal combustion engine. So it's something that's really bad. So something with a very, very high octane rating is very resistant to knocking. Something with a very low octane rating is not resistant to knocking. And then the last thing we talked about with our gasoline were our alternative sources of energy. And so this is pretty straightforward. We just had one little module on this, and basically I just want you to be familiar with the definition of what these alternative sources of energy are. So instead of gasoline, I should have that said. So for example, if we're talking about solar, I would expect you to know that solar energy, it works best when the sun's out and not at night, right, when the sun goes down. For wind energy, I would expect you to know that you need wind. You need wind, and it drives a turbine, but you need wind. If you don't have wind, you can't use wind as an alternative source of energy. So very, very topical, very simple, but I do need you to know those, just the bare minimum, so those 7 definitions, okay? All right, so now we move on to my favorite part, which would be considered the chemistry section. So number 2, chemistry. So this is more of our application section. So this is where we learned the chemistry part, the fun part, the awesome part, the exciting part. All right, so the first thing we did is we started by talking about the first law of thermo. So the first law of thermodynamics is that energy cannot be created or destroyed. It is only transferred. So our delta E, our change in energy, is always 0 if we're talking about the universe, okay? So we cannot create energy. This is not possible. Then we also talked about our second law of thermodynamics, okay? And so for the second law of the thermodynamics, basically what we're saying is that the entropy of the universe is always increasing. So our entropy of the universe is always going to a greater state. It's always getting bigger. So our energy is always spreading out. So if we ever talk about an example and you can smell something now that you couldn't before, this is because the gases have spread out. The gas molecules have gone up into your nose and you can now register it, okay? So energy transfer is first law, and if you can smell something or energy spreading out, or maybe it becomes disorganized or something of that sort, that's usually an example of the second law. Now, we also talked about just several different terms of thermodynamic terms, and so we need to get some definitions down, but I've also tried to organize this with a couple different equations in here. All right, so for thermo, the first thing we talked about was heat, which we know is represented by a lowercase q. It's a lowercase q. It is not capital. So we know that Q is equal to M times C times delta T. So Q is your heat, M is your mass, C or C sub S is your specific heat capacity, and then your delta T is your change in temperature. We also know that heat at constant pressure is equal to your enthalpy or your change in enthalpy. So Q sub P is equal to delta H. We also know that Q is absolutely in no way ever equivalent to temperature. They're completely different things. Q, which is heat, is the transfer of energy. It's going from one thing to another thing. Temperature is the kinetic energy at that specific moment in time. There's no movement. If you have movement, it's always talking about heat. And the last thing we did is we said that Q is not equal to work. Okay, so now our second thermodynamic term was work, and that has a lowercase w. Now, work is equal to force times distance, and so for work, the most important thing we realize is that this is considered organized molecular motion, where heat is unorganized molecular motion. So work is where all the elements, all the molecules are working together, and they're actually accomplishing a distance or accomplishing a goal. There has to be a starting point, and there has to be an end point. We also talked about temperature, which is definitely a thermodynamic property. It's a measurement of the average kinetic energy. We talked about entropy, which is our big S. Entropy is just our dispersal of energy at a given temperature. Dispersal of energy at a given temperature. You have to know that. Then we also talked about H, which is our enthalpy. Notice that I drew both S and H as capital letters. Does it matter? Yes, it is huge, huge, huge. Little s, little h, not the same thing. They have to be capital letters. Enthalpy, right, is just our transfer of heat energy at constant pressure. So we have our Q sub P is equal to delta H, or we could write delta H is equal to Q sub P. Okay, just by definition. You have to know this. This is not a thing you can just kind of forget. You need to know these definitions. All right, so that's just our basic vocab. Now, we then tried to quantify energy transfer. So this was much, much easier said than done. So now we had to try to actually determine what Q was, and the only way we could do that is by first establishing our units of energy. And so now remember, we had 3 main ones we've talked about here: joules, calories, and big calories. So we have our scientific calories here, which are our lowercase ones, and we have our nutritional calories, which are our capital C's. We need to remember that the calories we see on the back of a food package or gummy bears or whatever it is, those are your nutritional calories. 1 nutritional calorie is equal to 1,000 scientific calories. So you got to make sure that's straight in your head. Pay very, very close attention to those C's. All right, so then after that, we talked about endo versus exothermic. exothermic. And so I think we feel pretty good about these terms by now, but if not, just in case, endothermic is when you absorb energy. You need energy in order to go through a reaction progression. And exothermic is the opposite of that. You release energy. So you start at high energy state and you go to low energy, you're releasing energy, it feels really, really hot. These are definitely combustion reactions, which are exothermic. All right, now after that, we talked about this really awesome device called a calorimeter. And a calorimeter is something that allows us to actually measure these heat transfers. So we talked about two specifically. We have a bomb calorimeter, and we also talked about a coffee cup calorimeter. Okay, so our bomb calorimeter is done at constant volume, where our coffee cup calorimeter is done at constant pressure. Coffee cup or coffee cup, whatever. And so for our coffee cup calorimeter, remember you have two coffee cups, you put them together, then you stick your thermometer right in there, you can build it. It's very, very easy to build your own version of a calorimeter using coffee cups. It's not easy to build a bomb calorimeter. All right, so then the last thing we had here for calorimeters is this is where we introduce our term C sub S, or our specific heat capacity. And just remember, if you're ever lost, let your units tell you what to do. It's usually joules per gram degrees Celsius. So there's three components. If you're in grams, then your mass has to be in grams. If you're in joules, then your heat has to be in joules. If it's delta C, then delta T, then you have to be in Celsius. You just use this unit to let you decide what you're going to use when you're using the equation Q is equal to MC delta T. So watch those units, guys. Watch those units. I cannot drill that enough. All right, so then what we did is really globally, we talked about delta H of the reaction. So our change of enthalpy for our entire reaction. So this was huge. This was a really big section that we had. The first thing that we did is we tried to determine this in an accurate way. And so what we wanted to do is determine the true value. And when we do that, we're saying delta H of our reaction is equal to products minus reactants. And this is usually what we use when we're trying to do a graph. So we have something like this, and I tell you, here's your reactants energy level, here's your products energy level. We go from one to the other, and our delta H is right there. So it's your products minus your reaction. That's your delta H. Your product minus your reactants, and that is your delta H of reaction. There we go. All right, now alternatively, we can do an estimate, so a less accurate value. So the estimate is when we use that table of bond energies. So in that case, our delta H of reaction is equal to your bonds broken minus bonds formed. And we're going to do an example of this in just a second at the very end of this review, so just stick tight. If you have a question on this, we'll do it all together. But essentially, just remember, this is when you're drawing something out. So you're saying like, oh, I have this bond in hydrogen, I have this double bond in oxygen, I'm trying to create water, so I have to break my hydrogen bond, break my double bond here, and then I can create this single bond, okay? But please, please, please remember, you cannot ignore your coefficients with this. You have to keep your coefficients here, otherwise you'll get the wrong answer. All right, so now, what did we also do? We reviewed, because these were old topics, so you can't forget these. We've reviewed what hydrocarbons are. And so now for this module, I expect you to know carbon 1 through carbon 8, the names and the formula. So you have to know methane all the way through octane. I only expect you to know your alkanes, so your carbon single bonds. We also reviewed what a catalyst is. Okay, we talked about it in terms of activation energy and our delta H, and we reviewed what isomers are. Some of this was a super review for some people, but maybe this was brand new information for you. But just make sure you know what an isomer is, and make sure you can draw them, and make sure you can identify them. All right, and the last thing that we did, and we're going to do 1 or 2 example problems with this, was our dimensional analysis. Dimensional analysis, and oh my goodness, is this a challenging topic. And usually for students, it's something that they get right away, so they have to spend 0 time on it, or it's something that people have to study for hours and hours and hours. If you're in the second boat, I'm so sorry, but please do not give up. It is one of the most rewarding feelings to nail one of these dimensional analysis problems or a stoichiometry problem, so just fight through it, you guys. I know you can do this. All right, so there are 3 different categories you need to be able to do, or types of problems that you need to be able to solve using dimensional analysis. And the first one is a limiting reactant problem. Limiting reactant. So you need to be able to determine what your limiting reactant is. And if you can determine that, then you usually can figure out what your excess reagent is, or your excess reactant. And your excess is just the one you have left over. So you're sitting here, you've used up all your oxygen, you've got tons and tons and tons of hydrogen just sitting there. That would be your excess reagent. All right, I also expect that you would be able to determine your quantity of product that's generated. So if I said how much water is created from such and such hydrogen and such oxygen, I would expect you to determine the exact quantity of that water that was created. You absolutely need to be able to do that. So very, very basic stoichiometry. And the last one, and this is probably the most challenging, is I expect you to be able to determine how much of your excess reactant that you have. So what you do for that problem is you take your limiting reagent, you take your value of that, you convert it to mass of your excess reagent, and then you just take whatever was given. So let's say you have 10 grams, but you only need 1 gram to do the problem. 10 minus 1, you have 9 grams left over. There is a stoichiometry review sheet on Canvas. Please do this. I am begging you. Please do this thing. If you can do that review sheet, then I 100% promise you that you're going to nail this exam in the final exam. All right. That's all I have for the chemistry and context section. So what I want to do now is just go to those 3 problems and give you a chance to work through them. I'm not going to do any quizzing features. You don't have to do anything like that or submit an answer. That's not important to me. We're just going to kind of fly through this. All right, so take a second and figure out what this is. All right, were you able to get an answer and actually solve this problem? Hopefully, because this is definitely a skill you need to master. I could take this one question, put it right on the final. You need to make sure you know how to do this. So step number 1, if the chemical equation is not given for you, you need to write that out. But luckily it was for us. However, for this problem, it was not balanced. The first thing you had to do was actually balance it. So I would go through here and balance it. And if you do it properly, you should see 2, 3, 1, 3, and 3, okay? So now, the only thing you can do is start with what you know. So what we have to do is take 15 grams of ammonia and 15 grams of copper oxide and convert it to grams of nitrogen. So we have 2 different processes we have to do here. So let's start off with our ammonia just to keep it simple. So we have 15.0 grams of NH3. What we're going to do is convert grams to moles, and so we do that by using the molar mass. So ammonia is about 17 grams for every 1 mole of NH3. Now we're in moles of ammonia and we're trying to get to moles of nitrogen. And so we see for every 2 moles of ammonia, we have 1 mole of nitrogen. And we also know that for every 1 mole of nitrogen, diatomic nitrogen, we have 28 grams. So if you do this properly and solve it out, you should get an answer of about 12.35 grams of nitrogen created from ammonia. So that's one way. Now what we need to do is figure out how much nitrogen we can create using 15 grams of copper oxide. So we have the exact same process. So 15 grams of CuO. We use the molar mass to convert from grams to moles, and so we know copper oxide has a molar mass of about 79.5 grams, and this is per every 1 mole of copper oxide. Then we look at our chemical equation. We see there's 3 moles of copper oxide to every 1 mole of nitrogen, so we have 3 moles of CuO to every 1 mole of N2. The last step is to go from moles to grams, and for every 1 mole of nitrogen, we have 28 grams, again, of N2 diatomic nitrogen. And if you do this properly, you should type it into your calculator and get an answer of 1.76 grams of nitrogen produced from 15 grams of copper oxide. So now the last step is to decide, what is my answer? Is it 12? Is it 1? Do I add them together? Do I subtract? Well, the answer is it is just the smallest number. So 1.76 grams of nitrogen is all you can create if all you have to start with is 15 grams of ammonia and 15 grams of copper oxide. You are going to completely run out of your copper oxide before you will even, barely touch your ammonia. You do not need any of it, okay? So that's your first problem. Hopefully that makes sense. If it doesn't, stop and ask your teacher right now or shoot me an email. Number 2, go ahead and try it. All right, did you get it? Hopefully you did. This one was fairly straightforward except for one teeny tiny little spot that students usually make mistakes on, so that's why I use this one. So the first thing you have to do is decide what equation am I doing and what am I trying to solve. Well, basically what they give us is a heat component, so our 5.9 kilojoules. We have an initial temperature 25, a final temperature of 50, and we also have a specific heat capacity. And so right away I see the word calorimeter and I hear all these properties and all these variables that we just clarified or just announced, I guess we could say. And so we know we're going to use our equation of Q is equal to mc sub s times delta T. And so what we have to do now is basically just type in all of our numbers here. So our Q is our heat component. But the first thing I want to point out is that this is in kilojoules and our specific heat is in joules. So what we need to do is make sure that we convert one of them. And remember from before, I say we always let our specific heat unit dictate what we do. So we need to get our Q value into joules. So basically you just multiply it times 1,000. So we have 5,900 joules is equal to M, that's what we're solving for, times the specific heat of water, which is 4.184. That's a constant that never changes, and I will always provide this for you. You are not expected to know any of those constants. And then we have our delta T, which is our final temperature, so that was 50 degrees Celsius, minus our initial temperature, which was 25 degrees Celsius. And if you plug this in your calculator properly, you should get a mass of about 56.4 grams of water. Did you get it? If not, stop, talk to a teacher, shoot me an email, but you definitely need to make sure you get this one down. All right, we have one more that I want to do and let you give yourself just a little shot at it. And so here you go. Good luck. All right, did you get the answer? Hopefully you did. In case you didn't, let's just review it together. First of all, I want to say that this is very complicated, and this is going to be as difficult as it possibly would be for our exam. I will not write a question that is harder than what you just did. All right, so first thing you have to do, if the chemical equation is not given to you, you must write it. You must generate it. We were lucky, and it was given to us for us, so now what we have to do is balance it. And so hopefully you were able to do this, but you should have 1, 2, 2, 1, 2, and 2. All right, so now the second thing you do for this example is you draw every single molecule out. You have to draw them. And so what I'm going to do is just slide this over a little bit if I can and see if we can get a little bit more room here. All right, so the first thing we do is we have methane. So that's our CH4. So we have H, 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 and H. So there's 4 carbon-hydrogen bonds, plus chlorine, diatomic chlorine, that's pretty simple, plus fluorine. Diatomic fluorine, single bond there, goes to CF2Cl2. So we have F, F, Cl, and Cl, and I'm drawing it in the 3-dimensional structure, which is not necessary, but I'm a chemist and I like it, so I'm doing it. We also have HF, single bond here, and I'm just going to put it below so that we make sure it doesn't cut it off. We also have HCl. So now what you have to do is basically go through and try to create your delta H of reaction equation, okay, your mathematical equation. So what we remember here is whenever we're using our bond energies or our average bond energies, what we have is bonds broken minus bonds formed. Every single time. It's never products minus reactants or anything else. It is always bonds broken minus bonds formed. So what that means is that you have your delta H of reaction and you break apart every single bond that is on your reactant side. So the first thing I see is we're going to start with methane. I see 1, 2, 3, and 4 carbon-hydrogen bonds. So I have 4 carbon-hydrogen bonds per molecule, but you have to check up here. We only have 1 molecule, so we're good. So we have 4 carbon-hydrogen bonds. The next thing that I see is there's 1 chlorine-chlorine bond per molecule, but we have 2 molecules total, so we have 2 chlorine-chlorine bonds that we have to break. Then I see a fluorine-fluorine single bond, so FF single bond that we have to break. We only have 1 bond within the molecule, but there's 2 molecules total, so we have to do 2 times FF. Now these are all your bonds broken. So on the left side of the equation, those are your bonds broken. Your bonds formed are on the right side. So now, on the right side, what we see is we have 2 carbon-fluorine bonds, okay, per molecule, 1 molecule total, so we just do 2 here. We also have 2 carbon-chlorine bonds, again, only 2 carbon-chlorine bonds per molecule, but only 1 molecule, so 2 total. And then we have our hydrogen-fluorine bond. I'm just going to come below here so I make sure it doesn't get cut off. So now we have hydrogen-fluorine, so we have HF, 1 single bond per molecule, but 2 molecules total, so we have to use that coefficient 2. And then the last one is, again, a single bond between hydrogen and chlorine, but again, there are 2 molecules total, so we have to multiply that by 2. Now, the next step is simply just taking this chart up here in the upper left-hand corner and plugging in our actual values for this. So we have our delta H of reaction. We do 4 times our carbon-hydrogen bond. So I expect you to go over here. We can see that, I have cut it off. We can see that we have hydrogen right here at the top. We can see carbon right here on the side. And so when we come in here, we would see that our carbon-hydrogen bond is actually 413 kilojoules per mole. Okay, and so I'd expect you to use this chart to go through and have every single one. So for our carbon-hydrogen, we have about 413. And then for our chlorine-chlorine bond, we have something that is about, let's find it here. So here's our chlorine, and then we have another chlorine right there. So we have 242, so 2 times 242. Come on, pen. 242 plus 2 times our fluorine-fluorine bond. So again, come over here. So we have our fluorine that comes down here to our fluorine, so that's 155. Okay, 155. And then we subtract out our bonds formed. So 2 times our carbon-fluorine bond. So we have our carbon-fluorine, that is about 485. And then we have 2 times our carbon-chlorine bond. And so we have carbon here, chlorine 339. So 2 times 339. And then we have 2 times our hydrogen-fluorine bond. So our hydrogen is here, fluorine is here. We have 565. So 2 times 565. Oopsies. These take so long, don't they? 565. And then the last one, 2 times our HCl. So we have our H right here, chlorine down here at 432. Okay, so then you can do one of two options. I am decent at math, and so I usually just go straight to my calculator, but if that's not your thing, just use your calculator and type everything right in here. So do it by section. So do 4 times 413 plus 2 times 242 plus 2 times 155. And so you would see that your bonds broken section is 2,446. And then you're going to subtract that out from your bonds formed. So 2 times 485 plus 2 times 339 plus 2 times 565 plus 2 times 432, and you get an answer around 3,642. Okay, and the last step is to just do very, very simple math. So you have delta H of your reaction, plug it into your calculator, 2446 minus 3642, and your answer is negative 1,196 kilojoules of energy released per mole of methane burned, okay? So that's how you have to think of it. Hopefully this makes sense. Like I said, this is incredibly complicated and incredibly detailed, so if this was too much for you, please do not panic, but just slowly and methodically work through the problem. If you have questions, you ask your teacher. If not, email me immediately and we'll talk this through. Have a great week. Take care of yourself. Good luck on the exam and on the final, and drink water!